If I ask you to picture a high-power laser, the kind used for everything from really precise manufacturing to delicate eye surgery, even cutting-edge quantum research, you're probably picturing a huge lab, right? Full of expensive, complex machines, a whole dedicated room.
Yeah, historically that's spot on. These are short pulse lasers we're talking about, instruments that work with incredible precision, immense power, but they always had those three big downsides:
Hmm.
size, cost, and just complexity. It kept them pretty much locked away. They couldn't really, break out into fields that needed portability.
And that is exactly the problem, the challenge we are diving into today. We're looking at this remarkable leap forward from the University of Stuttgart and Stuttgart Instruments GmbH.
Hmm.
They didn't just tweak the tech, they basically took that entire massive setup, potentially more than doubled its efficiency, and shrank it down to the size of your palm.
Right. So our mission here isn't just to say, wow, it's smaller. It's to really get into the engineering. How did they actually solve that huge, long-standing conflict? The one between needing high efficiency for power, but also needing wide bandwidth for those ultra-short pulses. We want to break down how they did it and then think about what this new kind of compact precision means for things like medicine or, say, environmental monitoring out in the field.
Okay, and let's start with the headline number, because this really sets the stage for why this is such a game changer.
Hmm.
Right now, the standard for these powerful short pulse laser systems, they get about 35% energy utilization.
Mm.
You put in 100 watts of energy, you get 35 watts of useful laser light out, which means, what, 65% of the energy you pump in is just lost?
Yeah.
Usually as heat.
Yeah, it's hugely inefficient. And that 65% loss, it just makes the problem worse because then you need massive power supplies to start with and these really complex cooling systems just to deal with all that wasted heat.
Exactly. It forces the whole system to be enormous.
Yeah.
Now, this new team, the Stuttgart team, they aren't just aiming for a little improvement. They've shown in their experiments it's fundamentally possible, is the quote, to hit an 80% efficiency rate.
80%.
Yeah, compared to 35%. That's more than double the standard. That jump, that extra 45 percentage points, it means the infrastructure costs alone, like cooling and power, must just plummet.
That right there, that's the essential first step before you can even think about making it tiny. But to really appreciate the breakthrough, maybe we should back up a tiny bit. Why are these systems so critical in the first place?
Good point.
Hmm.
Let's break down the power we're talking about. What exactly is a short pulse laser? Why is being short so important?
Okay, so these lasers, they emit light in incredibly short bursts. We're talking nanoseconds, picoseconds, or even femtoseconds. A femtosecond is a quadrillionth of a second. It's an unimaginably brief flash of light.
A quadrillionth. That's just hard to wrap your head around.
It really is. But think about the effect, not just the number. Because that pulse is so incredibly brief, it lets the laser deliver a huge amount of energy to a very, very tiny area. The target before that material even has time to notice the energy as heat.
Ah, okay, so it does its job, like cutting or vaporizing, before the damaging heat can spread. That's the precision element.
Precisely. If you used a slower laser or like a continuous beam, you're constantly adding energy over time. That builds up heat. And if you're making a tiny, fragile electronic part or doing surgery on something delicate like an eye, that heat causes damage. It melts things, cracks things, contaminates the area. The speed, that femtosecond speed, lets you vaporize material or etch incredibly fine patterns with basically no thermal damage around it.
And based on the research, we use this super precise power for all sorts of high-tech stuff. We're talking ultra-precise material processing and advanced manufacturing, like micromachining tiny circuits, or drilling holes smaller than a hair without causing stress fractures.
And that's just one area. It's also essential for advanced medical imaging and for the extremely precise measurements you need down at the molecular level for quantum research.
So the technology is vital, indispensable, really, but the equipment is just massive. And that size and complexity, that was the main roadblock, right?
Absolutely. Professor Harold Geeson, who heads the institute involved, he pointed out that needing both high power and high efficiency is what fundamentally drove the need for these big, complex, expensive setups we see today. You're basically fighting physics and thermodynamics to get that unique combo of precision and power working efficiently.
And that fight is made way harder by starting with only 35% efficiency. Like you said, you're pumping in tons of energy, wasting 2/3 of it, which forces engineers to build huge cooling systems, use enormous complex crystals. It's a real catch-22.
Exactly, which is why that jump to a potential 80% efficiency is so revolutionary. It breaks that cycle, the cycle of needing more power because you're inefficient, which then demands more cooling and more size. it just spirals.
If you want to make a laser palm-sized, you absolutely have to crack that efficiency nut first. Otherwise, you don't have a useful tool. You've got, I don't know, a very hot paperweight. So, okay, let's get into the mechanics. How does this new system, they call it an optical parametric amplifier, right? How does it actually generate this super efficient, ultra-short light?
Yeah, it's quite an elegant process, really. It's all about converting light particles. The system uses what's called a pump laser. That channels light energy into a special crystal at the heart of the device. This crystal then acts like a transfer station. It takes that energy and feeds it into an ultra-short signal pulse. And in doing so, it converts the incoming light particles into infrared light.
Infrared light. Okay, and that's the key output here. Because those specific longer wavelengths let them do things, diagnostics, measurements, that you just can't do with visible light.
Exactly right. But this is where that core engineering challenge pops up. The one Dr. Tobias Steinl, the lead author, really focused on. It's this fundamental conflict between getting the quality you need, the shortness of the pulse, and getting the efficiency, the power amplification.
Okay, let's unpack that conflict because the solution here sounds really clever.
Right. So if you want to generate really, really short pulses, femtosecond level, that requires a very wide range of light frequencies, what we call wide bandwidth. And to get that wide bandwidth, you generally need special crystals that are inherently short and thin.
Okay, short and thin crystals for short pulses. Got it.
To get that really high amplification efficiency, pushing towards that 80%, you need the opposite. You need length. You need a long pathway for the light in the crystal, so the pump laser energy has a plenty of time to interact with and boost that signal pulse.
Ah, so there it is. Short crystals give you quality pulses, but they're not efficient. Long crystals give you efficiency, but maybe mess with the pulse quality or bandwidth.
Exactly. It's a fundamental trade-off. In the past, if you absolutely needed both high-quality pulses and high power, you had like two bad options, and neither worked well for making things small.
What were the old options?
Well, option one was just use a single, massive, highly specialized crystal system, very expensive, very large. Option two, which was maybe more common, was to try and link several short crystals together in a series, like beads on a string.
Okay, linking short crystals. Why was that such a problem? If one crystal is small, just line up a few. Seems logical.
The problem is the speed. Everything's happening at the speed of light, remember? To get efficient amplification across that whole chain of crystals, you need absolutely perfect synchronization. We're talking micron-level alignment between the pump laser pulse and the signal pulse as they go through every single crystal in that chain.
Whoa.
Any tiny drift, any microscopic misalignment anywhere along that path, and the energy transfer just collapses. You lose efficiency, you ruin the pulse quality. It's incredibly sensitive.
That sounds like a constant, high-maintenance synchronization nightmare. If you're trying to build something robust and portable, a delicate chain needing perfect sync is the last thing you want.
It's precisely why the tech stayed stuck in labs with stable temperatures and vibration isolation. And this synchronization challenge is exactly what the Stuttgart team solved with their new approach, this multi-pass procedure.
Okay, tell me how they cracked it. How did they get around that synchronization barrier?
They basically sidestepped the whole series problem. Instead of one long crystal, or lots of short ones lined up, they went back to using just one single short crystal, the kind that's great for bandwidth and pulse quality.
One short crystal. Okay, but then how do they get the amplification? How do they get the effective length they need for efficiency?
Here's the clever bit. They repeatedly run the light pulses through that same single crystal over and over again. They use a very precise setup of mirrors and optics inside their amplifier device. It sends the light pulse looping back and forth, hitting that same crystal multiple times on each pass.
Like doing laps.
Kind of, yeah. It effectively tricks the system. It makes that single short crystal act as if it were one long amplification path. They substitute physical length with intelligent repetition.
That sounds much smarter. And more stable.
Way more stable. And here's the crucial part, the step that was so hard before, between each pass through that single crystal. The system uses incredibly precise optical elements to perfectly realign the pump pulse and the signal pulse. This constant controlled realignment happens at just one point, over and over. It guarantees they stay perfectly synchronized every single time they pass through the crystal.
Okay, that sounds much more manageable than trying to keep 10 separate crystals perfectly aligned down a long chain. It's localized control.
It is, and the physical result, it's staggering. That clever, repetitive design let them get both the peak power and the pulse quality they needed, but in a tiny space. The sources say the resulting system generating pulses shorter than 50 femtoseconds takes up only a few square centimeters. It genuinely fits in your hand, and it consists of just 5 main physical components.
5 components. Wow, that's where the massive size reduction comes from. Just like Dr. Steinel said, this proves you can have extremely high efficiency and high quality short pulses without sacrificing bandwidth or needing massive complexity. They tackled that core conflict directly.
So yeah, we've gone from maybe 35% efficient room-size complex beasts to potentially 80% efficient palm-size 5-component devices. What does this huge shift actually unlock out there in the real world?
Well, the most immediate thing, as you hinted at earlier, is replacement. This compact system could potentially replace those giant, power-hungry legacy laser systems.
Mm.
That would dramatically cut operating costs, get rid of those huge cooling systems needed for all that waste heat.
And what's really interesting, too, is how versatile the core concept seems to be. The researchers made it clear the design is adaptable. It's not just locked into making infrared light. They can apparently adapt it fairly easily for other wavelengths, use different types of crystals, change the pulse durations. That tunability is a really big plus.
Right, tunability plus portability. That's kind of the magic combination, isn't it? Suddenly, this incredibly powerful and precise lab tool can potentially be carried out into the field.
Exactly. And if you connect that to the bigger picture, the small size and that ability to tune the wavelength, which is crucial for identifying different materials or chemicals, it just opens up entirely new portable applications. The researchers who have significant funding for this, as part of the Meyer Sweep project, they're explicitly aiming to build small, light, compact, tunable lasers for real-world use.
Let's talk about those applications because they really show the value of shrinking this down.
Yeah.
Medicine, for instance. What changes when you can bring a high-precision diagnostic laser right to the patient's bedside?
Well, think about it now. If you need some kind of specialized, high-res diagnostic, maybe detailed tissue analysis or advanced imaging with specific wavelengths, usually the patient, or at least a sample, has to go to the big central lab where the laser lives. With this tech, you could potentially take that diagnostic power right into the operating room, or maybe into a clinic or the patient's room. It could allow for much faster, maybe even non-invasive analysis right when it's needed. That could be huge for point-of-care diagnostics.
And then looking at environmental research.
Yeah.
The impact seems even more dramatic because those scientists are often working way out in remote places.
Oh, it could be transformative for things like chemical analytics and gas sensing. Right now, highly precise gas sensing often needs bulky equipment set up at a fixed site. But imagine having a portable device you can carry around, and you can quickly tune its laser wavelength. Environmental researchers could do rapid, on-the-spot spectral analysis, like tuning the laser to precisely identify and measure trace amounts of methane near a pipeline leak, or CO2 levels or other pollutants right there at the source.
Which was totally impractical before. You couldn't exactly drag a room-sized laser setup through a field or up a mountain.
No, not really, no. And the speed is key, too. Portability means real-time monitoring. Faster responses to environmental issues instead of collecting samples, shipping them back, waiting days for lab results. When you shrink the tool this much, you just fundamentally change the logistics of how that science gets done.
Okay, let's try and wrap this up. Synthesize the big achievement for everyone listening. Researchers took this incredibly powerful but historically massive technology, the short pulse laser, and first, they tackled the efficiency problem head-on, multiplying its potential power usage from a wasteful 35% way up towards a stunning 80%.
Right. And then through some really elegant engineering, that multipass trick that solved the old conflict between pulse quality and power efficiency, they radically simplified the hardware, shrinking it from something filling a room down to basically a 5-component device you can hold in your hand.
And that success, that miniaturization, it unlocks a whole new generation of portable precision tools, replacing heavy, expensive lab gear with devices we can actually use out in the real world.
Which leads to a final thought, maybe something for you to chew on, based on that versatility we talked about. Given that this new design allows for really precise and rapid tuning of wavelengths in a truly portable package, and we know that specific wavelengths are key to identifying specific chemicals, how might this specifically revolutionize the way environmental scientists do that rapid on-site analysis, detecting gases, monitoring pollutants, things that were previously impossible without hauling samples back to a fixed lab? The capability is moving out of the lab and into the field. What new discoveries might that enable?